Okay. Lesson 45, nuclear reactions. We will be able to balance nuclear reactions. So, balancing a nuclear reaction is very similar to balancing a chemical reaction. And you guys have been doing these for ages. So, this stuff shouldn't really be too brand new to you, but it's always good to get some practice. And I'd like to try and give you guys some practice before the end of this, class. So I've got some worksheets that I want you guys to work on, but we'll see if we get up to it, because I also want to try and teach you guys a little bit more for the basics. Now, tomorrow's class, we're going to be wrapping up matter. So as I said to you guys, we're going to be teaching matter in 7 periods. And what I'm essentially doing is I'm doing a double on the universe, a double on the standard model, and a double on fusion and fission. Now, the last one on fusion and fission should actually be pretty easy because you guys have studied fusion before, so fission before. You guys know about how radioactive decay. So it's not necessarily going to be, there's going to be some new stuff in there, but it's not going to be brand new. Another quick reminder as well, before you guys look at this and you're like, oh my God, you're trying to teach us so much, Mr. Greer. There is only going to be, I think, in total, 16 marks on the whole exam dedicated to this topic. You might be like, shit, 16 marks, that's a lot. The whole exam is out of 80 marks. So it's actually only a tiny sliver, so 20%, which is actually sizable, but 20% of the exam is going to be on nuclear, is going to be on like matter and this topic that we've been studying. And so, yeah, it's 20% is not insignificant, but it's also relatively small. So if you've spent this past week and a half and you're like, I haven't learned anything, then, you know, the worst case, you'll lose 20% from the exam. Best case is you probably picked up 1 or 2 things and the questions are going to be really easy. So don't stress too much. As I said, I would have preferred more time to teach you guys this, but this is what happens. What I want to do is first to go back a sec to have a look at what we studied last lesson. Last time I had you guys, we talked about the standard model. Now we're going to breeze through this super quick. So, you know, strap yourselves in, put your seatbelts on. We started off with the model of the atom, which you guys have seen before, time and time again. We didn't spend much time on that. We said that we discovered that you can divide protons into neutrons into small particles, and we came up with something called the standard model, which is it's smaller than a proton. And what these are, there are 17 particles, and they're broken up into 2 groups. These 2 groups are broken up into fermions and bosons. Fermions are firm. They make up matter, whereas bosons, they make up forces. So fermions are firm, they make up matter. So we started off by talking about the bosons. There are 4 bosons that we need to worry about. Then we've got the gluon, the photon, and the Z and W bosons. Both of these guys deal with weak force. The gluon is the glue, so that's the strong force. And the photon is going to be linked to the electromagnetic force. And so the idea is that these particles get exchanged between particles, and that's how they know that, you know, they're interacting with another particle. They'll be like, oh, cool, I've just received a photon, so that's how I interact. Now, there is no graviton, but there is a Higgs boson. What the Higgs boson does is it gives particles mass. You might be like, why is there not a graviton? Well, we actually think there is a graviton, but I did some research on the weekend, just as a quick little, you know, watch a YouTube video. We haven't discovered the graviton because the graviton is so weak that it'd be really difficult to find. That's what I read. That's what I watched anyway. Now, as for the fermions, the ones that make up matter, we've got 6 of them are quarks. Up, down, strange, charm, top, and bottom. Just so happens that up has a plus 2/3 charge, so does charm, so does top. But the down, strange, and bottom quark all have a minus 1/3. What that means is that if I wanted to make a particle, I would need more than one of these things in order to get a full charge. So how do you get more than one quark? Well, hadrons. Hadrons are made of multiple quarks. Mesons are 2 quarks, baryons are 3 quarks. Okay, cool. Here's a baryon. It's got 3 quarks. Here's a meson, it's got 2 quarks. Now the idea is that if you look at these, and this by the way, look at this. This is called a kaon. That's a down and anti-strange. So if you remember, a down is going to be minus 1/3, and an anti-strange, so strange is plus 1/3, so an anti-strange would be minus 2/3. So this has got a charge of minus 1. And we haven't talked about kaons. You might think, oh, well, do I have to memorize that? No, you do not. You just have to learn this idea that a meson is made up of 2 quarks, an anti-quark, a quark, and an anti-quark. You do not need to memorize any of them. You just so this is an example. This is not something that you need to memorize. It's just, hey, heads up. A pion, a pi plus ion is when you take an up quark and an anti-down quark. Here's another example. A kaon is when you take a down quark and an anti-strange quark. Doesn't matter. What about baryons? Baryons are 3. But there are only 2 stable ones, the proton and the neutron. 2 ups and a down, plus 2/3, plus 2/3, minus 1/3, and plus 2/3, minus 1/3, minus 1/3. They cancel out to give you 0 charge. Beautiful. We talked about antiparticles. They're just the opposite of regular particles. That was it. They just got the opposite charge. And when they meet, and a particle and an antiparticle meet, they annihilate. I talked about how the strong force and the weak force work over a very, very, very small distance. That was the key from this slide. Small distance. I talked about, the weak force is very weak, but not as weak as the gravitational. That's why it's going to be so hard to find the graviton, because it is so weak. It's so weak. It's funny, the gravity is weaker than the weak force. It's just it's a bit odd, but it doesn't matter. And then leptons. That was the last section of the fermions. So the fermions, again, the things that make up matter. Leptons. Leptons are super light. They interact with the weaker nuclear force. Electrons are leptons. So are muons, which are fat electrons, and tau, which are obese electrons. Electron neutrinos are like electrons, but they have no charge. They have virtually no mass either, so they pretty much do what the hell they want. We said that beta decay happens when an electron gets fired out of the nucleus, and then I talked about neutrinos. Quickly, I said they just fly through things, and I talked about discovering particles. And I said that particles can be discovered in the atmosphere, in cloud chambers, and then in super colliders. And that was it. That was the lesson. We did a lot of stuff last lesson, so that's why I thought I would go through it in about 10 minutes. So now, take a sip of my coffee. Now, next lesson, nuclear radiation reactions. Firstly, I'm going to talk about this. What is nuclear radiation? We've already talked about radiation. Radiation is when something is emitted from something else. We've already talked about thermal radiation, but I guess nuclear radiation is like a different type of radiation, but it's also similar. Nuclear radiation is energy released from the nucleus of an unstable element. By releasing this energy, the element becomes more stable. It is often broken down into new atoms. So, yeah, this is how I generally talk about radiation. So when you think about something, I talk about chemicals in the same way. This is the same way chemical reactions work. Essentially, you take something that is unstable. If you imagine a person trying to stand on one leg, and they're trying to stand on one leg, maybe they're holding like some heavy books, and they're trying not to fall over. You would say that they're unstable. But if they lose the books, then they probably be a lot more stable. So by losing these books, they become more stable. And so you might say, okay, well, what does that have to do with radiation? So if I've got an atom with which just have made up of lots and lots and lots and lots and lots of neutrons, and it loses a neutron, then it will become more stable overall. Just like how if I lose these books that I'm trying to balance, I'll become more stable. That's the example that I'm trying to say here. That's what radiation is. Radiation is the whole, and if I lose a little bit of matter, then I'll become more stable. Now, why things lose matter, that's a question for tomorrow's lesson. All we're focused on today is what is this stuff that we're losing. Now, you guys have studied this stuff already. What do you mean? You have studied a little bit of stuff on half-life, and you've studied a little bit of stuff on the reactions we're going to talk about. But let's talk about half-life briefly. Half-life is the time taken for half of the sample to decay. So if you've got a bunch of particles that are all unstable, oh, whoopsies. It's going to take, it's going to take some time for those unstable ones to reach more stable configurations. And the thing is that it actually takes, we can measure the half-life. So how long does it take for half of these things to change? And if you measure the half-life, you can actually get, after one half-life, you'll have 50% left. After two half-lives, you'll have 25%, because half of 50 equals 25. And after three half-lives, you'll have 12.85%, because half of 25 is 12.5, and so on and so forth. So you'll see that if we had 1,000, we started off with 1,000 atoms, then after one half-life, there'd be 500. After two half-lives, there'd be about, let's see, 100, 200, 250. So two half-lives would be about here, which is why you get 2450. This would be the half-life of this would be 24 days. So then after another 24 days, you'd expect to be about here at 74. So that would be 125. The one thing that I always like to remind students about half-life is, just because we know exactly how long it takes for half of the particles to disappear, doesn't mean we know exactly when. If you were to say to me, okay, sir, see this one in the bottom right-hand corner, when is that going to decay? Is that going to decay in 24 days, or is that going to decay in like 74 or 112 days? And I say, well, I don't know. I can only tell you that half of them will decay in 24 days, or whatever it is. This example on the right is 100 million years. It doesn't matter too much. So that's half-life. Now, when these things decay, what kind of decay can they have? Well, there are three types of decay. Oh, by the way, before we do that, the half-lives. Some half-lives are really long, and some half-lives are really short. But all of these different things are dangerous. You might be like, oh, but surely the half-life for a couple of seconds is more dangerous. It's like, yeah, but it also means that it's losing all of its radiation very quickly, so it will be relatively safe. Whereas if you grab something like a uranium-235, that's going to be emitting radiation like continuously over a long period of time. So they're all pretty dangerous, but they all just have the reason the top ones are more dangerous is not because they're more it's because they last for so long. If you make magnesium 23, it's going to be radioactive, but 11 minutes later, it's going to be completely fine. So yeah. Okay, so far, let's see. So far, I've just talked about what radiation is, so making things more stable, and half-life. You just can't, it's like how long it takes for half the stuff to decay and become more stable. Now, how does it do that? Well, there are 3 types of radiation. Now, this is the stuff that you probably learned in year 9, hopefully. I'm basing my assumption that you learned this in year 9, so I can actually go through this quickly rather than having to reteach you guys everything. Alpha radiation is the first one. Alpha radiation is when 2 protons and 2 neutrons leave an atom. They leave an atom. Really, it should say leave the nucleus, but we'll just say leave an atom. Alpha radiation has 2 protons, so therefore it must be positively charged. And you can write it as either alpha as 2,4, or you can write it as alpha 2,4 plus helium, because essentially, because there are 2 protons and 2 neutrons, it's essentially a helium atom. You're essentially emitting a helium atom. It's just emitting a helium atom that doesn't have any electrons. The daughter atom, now you guys may not have heard this term before, but the daughter atom means the atom that comes afterwards of alpha radiation will have a lower mass and atomic number. Its mass will go down because it's lost 4 nucleons, and its atomic charge number will go down because it's lost 2 protons. Now, because this is it is the most ionizing. Ionizing, by the way, means can rip off electrons and turn them into ions. That's why it's called ionizing. It is the most ionizing because it's positively charged. So if you fire that near, if you get an alpha particle near your skin, it will rip the electrons off the skin. But because it's so ionizing, it can be stopped relatively easily. You might be like, oh my God, it's going to be so damaging to my skin. It's like, yeah, but if you're wearing a jumper, it'll rip the electrons off the jumper instead. If you're wearing a shirt, it will rip the electrons off the shirt. In fact, if you just move it like, 30 centimeters away from your skin, it will rip the electrons off the air, so it won't even get near you. So yes, it is the most ionizing, but it can be stopped by air. So does that mean alpha radiation is safe if it's, can be stopped really easily? Well, this is again one of those double-edged swords. If I put alpha radiation in a box, and I put that box, in the same room as you, will you be safe? Yeah, probably you'll be fine. But if I was to put that alpha radiation into, I don't know, like a cup of tea and then give you that cup of tea to drink, then suddenly those alpha particles would be inside your body. Those alpha particles would then be ionizing everything inside your body, and you would die very quickly. This is actually how they killed a Russian spy in London in 2003. It may not have been 2003, but I'm pretty sure that's how they killed them, was with radiation poisoning. They just gave them a highly radioactive source. So that's alpha radiation. Now, Pardon me? After alpha radiation comes the next most well-known one of the ones we've actually talked about already, which is beta. Whoa. Yeah, you know what? Let's do this here. I meant to do this a little bit earlier, but we'll do this really quickly here. Just a quick refresher. You don't need to, you should know this already, but just so you know, the number on the bottom of one of these is the atomic number, the number of protons. So uranium has 92 protons. So that those two things are linked. If there was 91 protons, then I would have plutonium. I would not have uranium. 235 is the number of nucleons, which is the protons plus the neutrons. So for uranium, if I've got 235 minus 92, then that's going to be 200 and 143. Yes. Yeah. So that's 143 neutrons, which is a lot of neutrons. It actually says what? This is why uranium is one of the unstable elements. But yeah, just a quick refresher, because when we actually start to look at these things, we're going to be able, I'm going to need you guys to be able to be like, oh yeah, I know that. I know the top number is the mass number. This is again something that you should have learned in year 10 as well. But if you missed it in year 10, I just spoke about this to my year 10 students as well, because they just did periodic table. So, but if you did miss it, then here it is again. That's why here we refer to this as, Mr. Greer stuffed up this. That's wrong. That should be 4.2 like that, because the mass number should be on top. I'm sorry about that, ladies and gents. I apologize. Unfortunately, I can't really fix it up at the moment, but I will fix it up for the notes, so that at least you can look at it later on. Geez, I'm an idiot. Beta radiation. Now, we've already talked about beta radiation because we already discussed it when we looked at discovering particles, because we were talking about it. So let's talk about it. Okay, beta radiation is when an electron leaves the nucleus of the atom. Beta radiation is very small and is negatively charged. Beta radiation is written as the -1 beta 0 or 0 -1 E, the E being an electron. Beta radiation occurs when a neutron decays into a proton. And this can be stopped by most metals. Now, most metals can stop it. Again, is it ionizing? Hell yes, it's ionizing. It's an electron that's speeding at very, very high speeds. If that electron, if you've got yourself a happy little atom, right? You know, let's say we've got yourselves a happy little carbon atom, and he's sitting there and everything's happy, and then suddenly an electron just shoots through, right? And completely takes out one of your electrons. Then that's going to ionize that electron. That's going to ionize that atom. And so now that atom is going to be without one of its electrons. So yeah, it can pretty much just smack an electron out of the way. It's also got a charge, so it can also repel the electron when it hits it. So yeah. Now we did talk about this. I did say there were two types of beta radiation. Beta minus is the most common. In fact, that's why I've said beta radiation is when an electron leaves the nucleus, because that's what happens here. Beta plus is extraordinarily rare. It can occur, but it's very rare. And that's, again, one of the reasons why there is more. That's when a proton becomes a neutron. That's very rare. There is more cases of neutrons becoming protons. That's why, again, if you remember when we were talking about nucleogenesis in the universe, that's why we said that most of the particles were turned from proton. Both of these used to be the same amount, but then the bottom one became more rare, so we end up with more protons than neutrons. That's why there's so much hydrogen in the universe, but not that much helium. Last one. Let's come on. We've got some stuff to teach. Sorry, guys. Gamma radiation. So gamma radiation sits at the end here of the spectrum. Gamma radiation happens to be gamma rays. In gamma decay, or an excited nucleus decays into a stable nucleus by emitting energy in the form of gamma rays or high energy photons. It is represented by the symbol gamma and it's 0, 0. Why is it 0, 0? Because it's got no mass. It is just literally a wave of really bright, high intensity, high powerful light. Now, because it's got no mass, right, it can penetrate a lot. It can go through skin, it can go through your legs, it can go through paper, metal. You need to have it's not only is it has no mass, but it's also traveling at the speed of light. So it's very, very difficult to slow down. And it has no electric charge. One of the things that protects you from beta radiation is the fact that, hey, it's got an electron. So it's going to be repelled by other electrons. But gamma rays, they don't have this problem. You need many centimeters of dense material like lead to stop it from being absorbed. Because again, it does the same thing that beta radiation does. It's going to come across and it's going to go bang and smack into a electron, and that electron's going to be like, oh shit, it's going to fly off. And that's how it's going to ionize something. But I will let you know that it is the least ionizing of the three, because I guess that's the thing, it doesn't have a charge, so it's not actually a particle, so it's not as bad as ionizing as alpha or beta radiation. The thing about gamma rays, though, is that they can go really, really far. You can be like if you're in a room with a gamma radiation source, then you'll be in trouble because, yeah, sure, you can put it in a wooden box, but the radiation will get out of the wooden box and go through you. And most of those gamma rays will go straight through you without an issue. But every so often, one of them may smack into it and completely dislodge an electron. And it's like, oh, so what? Well, what if this carbon atom is one of the carbon atoms that's inside your DNA structure? And suddenly it breaks one of these base pairs. Well, guess what? You're going to have a mutation in that gene. You got a mutation in the gene, well, that might be fine. You might be completely healthy, or it might stop you from being able to, it might stop that cell from being able to, make insulin properly, or it might stop that cell from being able to die appropriately. So then you get like some kind of cancerous growth or something. So yeah, not a good thing to have happen. So this is the picture again. You got paper that can stop alpha radiation. Metal like aluminium foil can stop beta radiation. You need a lot of lead or a whole heap of concrete in order to stop gamma rays. So where are we at? What time have we got? We're at 9:35. I've only got like 10 minutes and a little bit left. Let's look at, let's see. We're gonna skip this, jump straight to this one here. So I want to show you guys this here. This is a quick picture of what we would refer to as a decay chain. What is a decay chain? Well, let's go have a look at this uranium-234 here. So if it loses to uranium-234, remember uranium is 92. So let's say we've got uranium, which is 92, and we've got 234. That can lose an alpha particle. And if it loses an alpha particle, then its mass will drop by 4. Because remember, alpha particles, and its atomic number will drop by 2, which will make thorium plus an alpha particle. I'm running out of room here, guys, so sorry about this. 2, 4. But let's have a look here. That's exactly what this graph, this is exactly what this is trying to show you. If you have a look, here's uranium-234, here's thorium. And you might be like, okay, cool. All right, that makes sense. That arrow means alpha radiation. But you can also see that, well, how did you know what's important about these axes? So the bottom one is the atomic number. We just saw the atomic number went down by 2. So we went from uranium down 2 in the atomic number 1, 2. And then the mass went down 4. So we went from 142, or this is the number of neutrons, sorry. This is not the atomic mass. Sometimes they do, but our number of neutrons went down by 2 as well. So we go down 1, 2. And so that means each of these green lines shows us how alpha decay works. For each of these green lines, we go down in the number of protons and down the number of protons and down the number of neutrons. But these red ones represent beta decay. Now, what happens in beta decay? Well, beta decay, if I look at polonium-214, so that's PO, and that's going to be 214, and that's going to be 82. Now, remember, in beta decay, a neutron becomes a proton. So that means that we're still going to have 214 as a mass number. But instead of having 82 protons, we're going to have 83 protons. And if we've got 83 protons, then that becomes bismuth. Plus, you also have to emit an electron and an antineutrino. And the reason why this is going down is because if you look, technically bismuth, right, has got 1 extra proton to the right, but 1 fewer neutron. So it goes down 1. And the idea is that as this chain goes on, we would get more and more stable. Now, one of the things that annoys me, ladies and gents, is that I'm just going to do this for a sec. One of the things that annoys me is that I had this really cool worksheet that I actually spent a lot of time last year working on. And normally what I would do is I give you this worksheet and you guys would be like, oh, I have to, work through it. And you guys would have to create one of these decay chains. But unfortunately, I can't give you this worksheet in person. And I tried my best last night to find a way to digitize this worksheet. And I couldn't find an easy way to digitize it. So instead, I've had to come up with a different plan. But I just thought I would show you that I did have a good worksheet. I have attached this worksheet to the Google Classroom in case you want to look at it. But yeah, let's do some examples. Now, we're going to do the top example together. We're going to do the top example and the second example together. But then I think maybe it might be good for you guys to get the other few examples to try on your own. But you may need a periodic table for the bottom two. There will be a periodic table attached in the exam. So just before you go, oh my God, but yeah. Let's look at the first one. So how do you balance a nuclear reaction like this? So in this question, we've got radon 222 goes to polonium 218. So we can see that the mass has gone down by 4. Can you guys see that? It's gone down by 4. So that means I need to make sure that whatever the particle that is here has a mass of 4, because I can't just create matter out of nothing. 4, 218 plus 4 equals 222. And the bottom, we've got 86 protons on the left. We've only got 84 protons on the right. So that means I need to balance out the protons. I need to put 2 here. What do you know? This is going to have to be an alpha particle, because an alpha particle has 4 protons, 4 nucleons, or a mass of 4 and 2 protons. So that means this is alpha decay. Cool. Let's look at this one, the second one. This is going to be a weird one, and I picked a weird one on purpose. So this one it's got a mass of 14 and a mass of 14. Okay, the mass hasn't changed. That's okay. If the mass hasn't changed, that must mean that the mass hasn't changed, and that must mean that whatever is being emitted has 0 mass. Okay. But we've gone from 7 protons down to 6 protons. So we've actually lost, we've got +7 here, and then we've got +6. So if I want to balance this out, right, this might be a little bit weird. You have to have an extra +1 charge. So here we've got 2 plus 84 equals 86. Well, then 6 plus 1 will give you 6 plus 1 will give you the 6 plus 1 will give you the correct answer. But you might look at that and think, well, that's not what an electron is. An electron is not a +1 charge. So this must be an anti-electron or a positron. And then we can balance, whenever you've got an electron, whenever you've got this kind of decay, you also need to add a neutrino, and that's it. This is actually beta plus decay, because it's got a +1. And again, we're doing the same thing. And again, firstly, I would wish that I had more time to teach you guys this. We're doing the same thing that we would normally do, that I would do with the other one, is that in this one, I made sure the bottom number's balanced. In this one, I need to make sure the bottom number's balanced and the top number's balanced. Now, the one below here, I've got 137 goes to 137. So I've got 0 mass, and 56 goes to 56. So I've got no change in charge. Ladies and gents, quick question to the chat. What is the only particle that has no mass at all and no charge? Can someone tell me in chat or out loud? What particle, what decay has no mass and no charge? Gamma. Thank you, Wim. Gamma radiation. So this is an emission of gamma rays. Job done. That's it. Let's look at technetium. Now, technetium goes from 98 to 43, and we're losing an electron. In this case, we know that we know this is beta decay. This is your usual beta decay because we're losing an electron. So if we want to balance out this charge, what number should be in the bottom left? Let me see if I can get you guys to tell me in chat. And I know that there is only about a minute left, so 2 minutes left. So we're going to try and wrap these last 2 examples up really quickly. What number should be on the bottom left? if I've got a -1 on the right-hand side? Bao's guessing 42. Good guess, Bao, because you've gone. No's guessing 44. The answer is 44. And the reason is because if I have 44 here, right, then that means I can say, well, 44 minus 1 equals 43. All these numbers on the bottom equal the numbers on the left. If I look at the top, I've got 0 and 0. So that means this has to be 98. So whatever I've got is I've got an extra proton because technetium has added a proton. So what we need to do now is all we need to do now is find out what element on the periodic table has 44 as its atomic number. That would actually require me to do some research. But if you guys want to quickly look it up for me as well, then that would be appreciated. Atomic number 44. Ruthenium, Ru. Beautiful. Done. Cool. So that is our answer. So Ru, ruthenium. And with this last one, in this case, we don't know what the parent atom is, but we can work this out. At the bottom, we've got 90 and 2. So the bottom number is going to be 92. At the top, we've got 4 and 30. So the top number is going to be 234. I just add those together. And I happen to already know what element is 92 on the periodic table. It is uranium. So this is uranium-234 undergoing alpha decay.
Sir, it's 9:48 already.
Yeah, no. Look, look, I just finished. Look, I was just finished. I'm done. Calm down. All right, that's it, ladies and gents. Thank you very much. I know that you guys need to go. I am ending the stream here.